The Collatz conjecture is notoriously chaotic. You take a number, apply a simple rule, and watch its orbit bounce wildly. But what if there is a way to step outside of that chaos? A framework where that infinite, unpredictable looping snaps into focus as a rigid, static grid. Running computer simulations for billions of steps can show us patterns, but a simulation is not a mathematical proof. To prove global structural properties of generalized Collatz maps, we cannot rely on unbounded iterative tracking. We need a different language entirely. The Symbolic Branch Collatz program translates the problem from tracking numbers into analyzing exact local step equations. Within this equation, we track three variables: our state, xi, the itinerary step, epsilon I, dictating the path, and a sequence parameter, the carry, ni. The objective of Part 1 in this research ledger is to establish a definitional bedrock. We are building a system that entirely bypasses the need to calculate the local iteration step by step. Instead of tracking a single path as it evolves over time, we fix the itinerary and map the sequence data to a global two-adic valuation structure. By encoding these local sequence choices into what we call a primitive weight system, we create a translation bridge. Infinite orbital loops are converted into static, solvable linear Diophantine equations. We start by defining our base symbolic parameters. We fix a sequence length h and an itinerary epsilon. This itinerary is simply a string of binary elements, zeros and ones, of length h. Alongside the itinerary, we define the carry word, n. This sequence is strictly dependent on the itinerary step. The logic dictates that ni must be selected from the set containing 0 and epsilon I. If epsilon I is 0, it forces that carry to be 0. The implication here is absolute. Whenever the sequence encounters an even step, meaning epsilon is 0, the system is strictly constrained. It must yield a 0 carry for that phase. We then feed these choices back into the local step equation. That equation applies a base multiplier, a directional shift, sigma, which selects whether we are in the 3x plus 1 or 3x minus 1 system, and subtracts the carry multiplied by an integer modulus, m. Look at how this equation cascades. We can map the state evolution across the first few sequence steps, moving algebraically from x0 to x1 and on to x2. At each individual node, the unique combinations of epsilon and the carry parameter n precisely dictate how the variable x transforms to the next state. But there is a severe limitation to analyzing the math this way. While node-by-node tracking is mechanically accurate, this hyperlocal view obscures any global arithmetic patterns hiding within the sequence. To escape the constraints of step-by-step local dynamics, we have to pull back. The variables driving these micro-changes must be abstracted into continuous, overarching global counters. We abstract the local itinerary by defining specific phase counters. First, we define O, the total number of odd phases across the entire sequence. Next, we define a localized counter, O plus I. This tracks the exact number of remaining odd steps that occur strictly after index I. These counters allow us to introduce the foundation of the ledger's entire algebra, the primitive weight system, denoted as Wi. As you can see in this equation, the weight relies on isolating the 2 to the power of I plus 1 factor from the 3 to the power of O plus I factor. By defining the equation this way, the base 2 component acts as an explicit index tracer.
It locks the exact step position, I, directly into the arithmetic value of the weight itself. Once the weights are established, we derive two new variables, s, a function of the itinerary, and k, a function of the itinerary and the carry. Notice how s and k are constructed. They are pure linear functionals. They are simply sums of the primitive weights we just defined. This is a deliberate structural choice. Standard approaches might try to extract s and k simultaneously from the outputs of the iteration. Defining the weights first flips that logic. Establishing the primitive object prior to the linear functionals isolates the two adic properties of the sequence. Because Wi is explicitly defined, every downstream valuation argument becomes mathematically transparent. We can now execute an algebraic unrolling. Through induction, we collapse h discrete, localized steps into a single global equation connecting the final state back to the initial state. If we want to identify cyclical behavior in the system, we have to enforce closure. We do this by setting the terminal state, xh, exactly equal to the initial state, x0. This leads us to define the expanding branch term, b, which we calculate simply as 3 to the power of h minus 2 to the power of h. By substituting our closure rule and that new branch term, the long inductive sequence reconfigures itself into a static format. Km minus bx0 equals sigma s. This is the affine endpoint identity. It operates as a semi-linear Diophantine equation that strictly governs the endpoints of the dynamic loop. To solve it, we apply a reduction sequence. We extract the greatest common divisor of the carry functional k and the branch term b, labeling that divisor d. Dividing the equation by d yields a set of unique parameterized integer rays for the modulus m and the state x0. By reducing iterative loops into finite arithmetic intervals, the system parameterizes every possible integer ray for a fixed Collatz branch. No dynamic simulation is required. We recall our primitive weight system's two adic properties. The valuation, v2, equals exactly I plus 1. Because any power of 3 is inherently odd, it contributes 0 additional factors of 2. That strict parity rigidly locks the two-adic valuation to exact non-cancellation lemma is our structural bedrock. Summing larger powers of 2 will always fail to cancel out a strictly smaller power of 2. Formally, a term possessing the exact lowest two-adic valuation cannot be cancelled by sums of larger valuations. Embedding this classical algebraic fact directly into the weight cocycle creates a mathematical framework that is unbreakable. This non-cancellation engine ensures every bit in the carry word n has a unique impact on the final functional k. Because each bit corresponds to a weight with a unique lowest two-adic valuation, the resulting sums can never collide. This guarantees carry injectivity. This logic also applies to the return maps. Because denominators grow by exactly the sequence period at every iteration, the non-cancellation lemma prevents an orbit from returning to a previously visited state. This guarantees critical orbit disjointness and proves kneading sequences never repeat. By isolating these two-adic valuations, the framework converts chaotic trajectories into a rigidly deterministic structure. The underlying arithmetic remains permanently locked.